So for our presentation, we are going to present the paper Prediction of the transverse elastic modulus of unidirectional composite by an artificial neural network with fiber position and volume fraction. Here are the outlines of the presentation. Introduction, numerical modeling of RVEs of unidirectional composites, artificial neural network, results and discussion and conclusion. Conventional unidirectional RVEs modeled with fibers and matrix have shown high prediction accuracy for mechanical properties in fibers' longitudinal direction, but they have shown some deviation in transverse direction. To predict the transverse strength and transverse elastic modulus, more sophisticated modelings of composite materials were conducted recently. To make highly accurate predictions, it is necessary to generate many FE-RVE samples containing the microconstructor of composite and to evaluate the material properties in a statistical manner, leading to a high computational cost. To overcome such problems, this work aims to provide a simple data-driven model for prediction of the transverse elastic modulus of UD composite. An ANN model was employed with the input dataset consisting of fiber positions and VF, and the output dataset including the effective plastic elastic properties obtained by CHS. The accuracy of the proposed method was confirmed by comparing the prediction result and the FE simulation result of several test datasets having random fiber positions. The results indicate that the proposed approach is simple and powerful compared to conventional ML approach based on image pixels with CNN combined PCA. Numerical modelings of RVE of UD composites. To generate RVEs with VF of 40%, 50% and 60%, the RAC algorithm was adopted. The RAC algorithm, uh, in the center fiber is first randomly generated. The next fiber is placed near the center fiber with a random orientation angle. This is repeated until there is no space around the center fiber. Then the current center fiber is replaced with a new one. This process is repeated until the current VF approaches the reference VF. The number of fiber was set to 93 and size of the REV was set to 10 micrometer, which is sufficient because 30 fiber with VF of 50% in the RVs have been proved to be sufficient to represent the microconstructor of UD composite. The Abacus Python script was used to generate the corresponding FE model of RVEs composed with fiber and matrix. RV generation using RAC algorithm. A total of 200 RVs were generated for each VF shown in the figure. To confirm the randomness of RVs in this work, it was checked by computing spatial metrics such as nearest neighbor orientation, Ripley's K-function, and paired distribution function. Evaluation of effective material properties by CHS. Fixes of periodic displacement boundaries conditions were applied to the RVEs to compute the effective elastic modulus by CHS. After that, the constitutive matrix was calculated through post-processing with element-wise stress and volume. which were converted into the effective elastic modulus. For numerical analysis, the E-glass fiber and MY750 matrix were used. The properties of the two constituents are isotropic and is shown in the figure. Artificial neural network. In this study, we used a feed-forward network (FFNN), which is most common and simplest type of ANN. ANN model was developed by using neural network fitting tool in the MATLAB Deep Learning Toolbox. The NN model consists of input layer of having 187 input nodes, XY coordinates of 93 fiber centers and VF, several hidden layers and output layer having 3 output nodes in terms of transverse elastic modulus, in-plane shear modulus and out-plane shear modulus. Here we can see a simplified version. Input uh, is, is the volume fraction of fiber location. Artificial network, neural network, and output is the transverse stiffness, in-lane shear modulus, out-of-plane shear modulus. In artificial neurons, it is in the hidden layer is used the sigmoid in the all artificial neurons in the hidden layer use sigmoid function as a nonlinear activation function, and output layer use linear transfer function. The ANN model was trained by scaled conjugate gradient backpropagation algorithm. The mean squared error, correlation coefficient, and relative error were calculated to check the accuracy of developed ANN model as follows, where N, Y, and Y bar denote the number of dataset, FE simulation, and um, ML prediction values respectively. The NN model was designed to have 4 hidden layers comprising 300, 300, 200, and 100 neurons through several trial and errors. 600 RVE samples were divided into 3 groups. 80% of the sample were used for training the ANN model, 10% were used for validation, and 10% was used for test dataset. Through many training iterations, the optimal ANN model having minimum MSE was developed. Result and discussion. Preparation of preparation of input and output dataset. In input and output dataset, RVE samples for each VF of 40%, 50%, and 60% were generated by RSE algorithm, and they were analyzed by CHS to evaluate 3 transfer elastic modulus. For training of ANN model, XY coordinates of 93 fiber centers and VF of random RVs were used as input dataset. The effective elastic modulus of composite material was set as output dataset. ANN modeling, training, validation, and test. The seventh ANN model showed a minimum MSE between the ANN prediction and the test dataset not used for training or validation. The MSE history of seventh ANN model was investigated according to the epochs. After the 125th epochs, the training process was stopped because the MSE converged to certain level, which means that the error was minimized. ANN modeling result for training, validation, and test. The prediction performance of developed ANN was checked with the test dataset by relative error. The regression plot of training, validation, test, and the total dataset and um, the total dataset and VF. Here the solid black lines are reference lines where the output value of ANN model is precisely matched with the corresponding FE values. To investigate the effect on the number of input datasets, the prediction by ANN model is conducted according to the number of input datasets 50, 100, and 20, as shown in figure 7, 9, and 10. The minimum R value of prediction in test dataset by ANN model were 0.39, 0.92, and 96 for the number of samples 50, 100, and 200 respectively. The R value for all the result is over 0.96, which indicates a proper fitting between the related FE simulation data and prediction of ANN model. It was concluded that the proposed ANN model was trained and accurate enough to predict the mechanical properties of the composite material. Here we can see the results. The ML prediction is plotted in the y-axis and FE simulation is plotted in the x-axis. And the dotted line is the reference line, and we can see the fit. And this is the fit for um, the model when we are using 50 samples or VE samples as the input. And here is the result of the prediction and fit when we used 100 RVAs as sample to train the model. This work provides a scheme to predict conclusion. This work provides a scheme to predict the transfer elastic modulus of UD composite with an ANN model. To verify the performance of proposed approach, prediction example of UD composite were obtained. Its accuracy was evaluated in terms of MAC, correlation coefficient, and relative error. The results confirmed that a high correlation was achieved with low error. This contrasts with the convolutional ML based on CNN or data reduction technique, such which must extract the feature from raw image data to heavy pixels. The approach will be extended to more complex nonlinear or arbitrary fiber shapes to predict various mechanical properties, including mechanical strength, which include interfacial layer and interfacial property.